when you look at a golf course, you probably don't think of it as a set of vertices linked together by a series of edges. Well, by now, you'll have realized that graph theory provides a useful language to analyze a surprising variety of situations. If we take a typical golf course, it essentially consists of a series of fairways and greens. These can easily be described in terms of a graph. But let me show you what I mean. As far as the vertices are concerned, they're just the greens. This is a 9-hole golf course, so we've got just 9 vertices. Then from each green we have a fairway leading to the next hole. And the fairways give us the edges of a diagram. Now if you add up the lengths of all the fairways, you're going to get a total distance of 2,550 yards. Now this is nothing like the shortest possible route, because the course builder's aim is quite the opposite of that. He wants to lay the course out to make good use of the limited amount of land available to him. Suppose, however, you wanted to install a sprinkler system to water the greens. How would you lay the water pipes? Well, the first thing is that you're now only interested in the greens themselves. The fairways are quite irrelevant. It's reasonable to assume you'll want to use the shortest possible length of pipe. And so the answer is to construct a minimum spanning tree like this one. And to find this tree, you could use the greedy algorithm, which you've already met in section 8.2. And you'll find you need, in fact, just 1,550 yards of water pipe. Now, in this case, the greedy algorithm leads us to the optimum result, but it won't always do so, as we shall see. We're going to look at other algorithms which also make use of the special nature of tree structures. And we're also going to concentrate in this program on a problem in which, once more, we're considering pipelines, but this time a problem in which the economic gain of laying the optimum pipeline structure is vastly more significant than any saving you're likely to make on sprinkler pipes. The discovery of large deposits of oil and gas in the North Sea brought to Europe a major new technology. Not only did the oil and gas need to be extracted from beneath the sea floor, it also needed to be transported many tens of miles to the nearest shoreline. Rigs now punctuate the North Sea, and we can regard them as vertices of a graph, just like the golf holes we looked at earlier. But now the edges of the graph are pipes which lie along the seabed, channeling the gas or oil between the rigs or the main feeder lines to the shore. The cost of laying offshore pipeline is considerable. In 1980, it was around £750,000 for each mile. Now, there were two types of technology in common use. The more traditional method of pipe laying uses supply boats to ferry sections of pipe out to a lay barge. This operation requires many vessels, because the floating supply boat has to be constantly restocked by smaller boats from the quayside stocks on shore. The other method, which is used only for narrower and more flexible piping, employs a special technique in which the pipe is joined together and wound onto a large reel. Then the ready assembled pipe is carried out to sea by a special cotton reel boat. And this itself is a very expensive investment. Starting from one of the rigs, the pipe is unrolled from the reel and it's gradually fed down to the seabed. With both types of pipe laying, the processes involved are complex and costly. The pipelines, which have to be buried beneath the seabed by special trenching techniques, must endure for many years and be well sealed and stable. They must withstand the effects of the pressure and the corrosive elements of the sea. And much attention is given to the joining together of pipe sections. The pipes are coated, beveled, and carefully lined up before going through up to 6 welding processes. Rigorous checks are made at each stage, including the use of X-ray film. The joins are then wrapped with an adhesive primer layer, and a steel sheet is strapped over them before they're filled with melted mastic and finally laced up ready for use. Now, although both types of pipe laying are expensive, broad diameter pipe is a more costly commodity, and any saving in both diameter and overall length of pipe can soon run into many millions of pounds. And it's this choice of pipeline layout and pipe diameter that is the center of our problem. Now, we're in fact going to concentrate on gas pipelines rather than oil, because a very interesting study was carried out in the United States on this. But to set out the problem, let's use a number of wells in the North Sea by way of example. Now, the first observation is that to avoid laying any unnecessary pipes, you'd go for a tree structure, just as we did with the sprinkler system. And so we have basically here a north-south line with the rigs linked to it and a feeder line to the shore. But that's not the end of the problem, because as we've seen, there's a choice of pipe diameters. Now, the smallest pipe can be laid relatively quickly and it's cheaper. Sometimes you may want to use larger pipes because you might want to cope with a big gas flow, for instance. However, you're going to be anxious to use the small pipe wherever they're adequate to cope with the flow. Now, there's one further assumption, and that is that the wells are being developed or coordinated at the same time. In other words, that a tree is being designed from scratch. Now, this proved to be just the situation that existed in the Gulf of Mexico in the late 1960s. Here, the oil rigs were being developed throughout the Gulf and in a more uniform pattern than we find in the North Sea. All these black dots here are in fact rigs. So you see, we do here have a very interesting problem. Now, a group of engineers and mathematicians in the United States noticed that in the design of good gas pipeline systems, there was a tree problem that warranted solution. In fact, the study was selected as part of a federal government program. And a leading member of the team was Dr. Howard Frank, who now leads a company in New York specializing in network analysis. And we asked him to recall for us how he and his colleagues set about solving the problem.
The problem breaks up into two fundamentally different problems. The first one is, suppose I had this network. Suppose, for instance, I knew this was a network I was going to build, this exact tree structure. First problem would be to determine the costs and associated diameters of each of the pipes within the network. To do that, I would have to design the network in such a way that I met the crucial variable, that is the pressure constraints at the gas fields and at the onshore collection point. For example, if I delivered the gas with a very low pressure, then I would have to spend a very large amount of money at the onshore point to recompress the gas for transshipment in. If I delivered the gas at a very high pressure, because of the fluid dynamic equations governing gas flow, I would have to spend a very large amount of money for the actual pipeline sizes themselves. So consequently, my design problem is a compromise of picking the right size diameters to meet the pressure constraints with a minimum cost. If I could solve that problem, I have a second problem. That is, what is the proper arrangement of pipelines in terms of locations? For example, I have a pipe going from here to here. I could just as easily have made that pipe be replaced by one going from here to here. Selecting the right topology, that is the right configuration of pipes, is itself a difficult problem. If you can't solve the first problem, then you clearly can't solve the second problem. So we decompose the problem into two separate problems. First, the design of the diameters. Second, the actual design of the configuration of the network. In doing so, we utilize the fact that this is a tree type of structure. And in fact, the major breakthrough is recognizing that it was a tree, and a tree had certain properties that general networks do not have.
So Dr. Frank's approach revolved around breaking the problem into two parts. First, take a given tree and find the optimum diameters for the pipes. And second, having set up a computer program for the first part, vary the tree and try to find a better layout. Now, to follow the first part, we need to know something about gas flow down a pipe. Now, the flow of gas depends not only upon the diameter d, but also upon P1 squared minus P2 squared over L, where P1 is the input pressure, P2 is the output pressure, and L is the length of the pipe. So suppose we're laying a particular pipe of length L, and there are two factors you've got to consider. There's the pressure squared difference, that's P1 squared minus P2 squared, and there's the total cost of manufacturing and laying a pipe of diameter d and length L. Now we can reduce the cost by choosing a small diameter d. But you've got to suppose that the pipe is going to be required to carry a certain flow of gas. And this is the catch. You see, if we make d too small, then the pressure squared difference may have to be increased, probably artificially, in order to maintain the flow. And that means using compressors to increase the pressure. And they're expensive, both to install and to maintain. So how can we decide which diameter of pipe to use? We have to balance the cost of the pipe against the cost of compression. Well now, pipe is available from the manufacturers in only a limited number of sizes. Let's suppose that there are, say, 7 diameters to choose from. The real problem for Dr. Frank and his team is to reduce the number of choices to manageable proportions. You see, in theory, you could evaluate every combination, but in practice this will be quite impossible. Now, the trick which Dr. Frank found was to develop ways of simplifying the problem by discarding all but a few combinations of pipe diameters.
The process that we developed essentially started at the pendant node part and collapsed these 3 branches into a single equivalent branch with a set of possible diameter combinations and a set of associated costs, which were the only ones that could possibly be in the optimal assignment. Once those were collapsed, you could replace these 3 branches by a single equivalent branch, thereby achieving the second configuration, that is, a node with 2 branches incident to them. We then developed a technique called a serial merge, which showed us how to collapse situations like that, that is, combine 2 branches incident to a given node into a single equivalent branch. Once we did that, we would now arrive at a node with 3 or more branches incident to them. We would then use the same technique that we developed before, called a parallel merge, to combine them again into a single branch. And we could do that for every element and path on this tree, thereby at the end arriving at a single branch with an equivalent set of diameters and costs associated with them. The practical part was to eliminate huge amounts, huge numbers of diameter combinations without ever examining them. That was the real breakthrough. So the first part of the problem was to pick a specific tree structure. How we got that tree structure is a separate issue, which I'll discuss in a few minutes. But to pick a separate tree structure, specific one, optimize the diameters of the branches in that tree structure.
You mentioned a technique which you called a parallel merge. Could you give us some idea of how this works?
Perhaps I could illustrate it in the following way. Let's examine this figure again, and let's focus just on this section of the network. And in fact, what I've done is I've blown that up so that we can examine it in detail. And now what I have is a node with 3 branches incident into it and 1 branch out of it. The 3 branches we're going to deal with are branches B1, B2, and B3, which will be collapsed into a single equivalent branch. To begin with, what I do is note that I have a flow equation. That flow equation relates to pressure square differences to the diameters of the pipes. And for every possible diameter of a pipe, I could compute the pressure square difference for that pipe. Also, since I know the length of the pipe, if I know the diameter, I can compute its cost. So I can make up a list of pressure square differences and costs for each possible diameter associated with pipe B1, with pipe B2, and pipe B3. And as a matter of fact, why don't we examine some potential lists? 2 rows, PSQ standing for pressure square difference, and PCost standing for the cost of the pipe. Now clearly, as the diameter of the pipe went up, its cost would go up, but the pressure square difference would go down. Now the second thing to note is that in a tree structure, if I have a certain pressure here, there's a pressure difference across branch B4. The pressure at this point is the same for that pipe, or that pipe. And clearly, since my problem has a maximum pressure constraint, the pipe which has the maximum pressure square difference across it will be the one which is on a critical path. Critical path meaning that's the one which has the greatest pressure drop across the entire path. Okay, let's examine this list. There's a very important point that now comes out. The greatest pressure square difference with the smallest assignment of diameters to each of B1, B2, and B3 occurs on pipe B2. That is right here. And the important point to notice is that I can immediately conclude that if pipe B2 has the smallest possible diameter, then I never need to have anything other than the smallest possible diameter on pipes B1 and B3. I can't relieve the critical pressure point, and I can only spend more money. What I've then done is I've eliminated having to examine those possible diameter combinations. So let's examine what happens if I have the second smallest diameter for pipe B2. That has a pressure score difference of 139. 139 is greater than 120 and greater than 94. Therefore, if I have the second smallest diameter for pipe B2, I need never have anything other than the smallest diameters for pipe B1 and B3. So let's move on. Let's examine the third possible smallest diameter for pipe B2. And here that has a constant of 14, a pressure score difference of 118. Notice 118 is smaller than 120. It's larger than 94, but 120 is the largest here. So I have another conclusion. If pipe B1 has the smallest possible diameter, then pipe B2 need never have anything other than the third smallest diameter, and pipe B3 has the smallest diameter. In this way, I can promote these indices one at a time, examining various combinations, and with no more than, in this example, 19 steps, have all possible diameter combinations that could conceivably be within the optimal assignment. What I've done is, since I had approximately 350 possible diameter combinations, I've eliminated about 330 of them without having to inspect those possible diameters. That is the critical point. The practical secret of this is that this process can be done very quickly with a computer for a very large network, and in comparison to the exhaustive search, makes the whole problem feasible.
So that must mean it would be quite easy for you to compare the relative costs of alternative tree structures.
Exactly. And in fact, that's the critical element of the second part of the problem. That is the optimization of the tree structure as opposed to the diameter assignments on a tree. And to see how we went about that, let's look at an actual realistic example drawn from the Gulf of Mexico. This network, by the way, happens to have a cost of around $111 million over its lifetime. That includes both operating and capital investment costs. And you can see here's the onshore compression plant, and this is the arrangement of pipelines within the Gulf. Your initial suspicion would be that the way to do this is to solve the classical minimum spanning tree problem. That is, install the pipeline network, which has essentially the minimum total length of miles of pipeline in it. And in fact, if we had no pressure constraints, and if we had only one size diameter, that would exactly be the solution to the problem. Unfortunately, the pressure constraints and the multiple diameters for each possible line make the problem much, much more complicated than the minimum spanning tree. And in fact, what we had to do is find a technique which is called locally optimal. Let's illustrate that for a second. This network, which, as we said, costs $111 million, has a line between this point and that point. I could have, for example, examined that configuration. And in fact, if I had, I would suspect that that configuration would be more expensive. That's because this line is shorter than the line I just added. Well, in fact, the reverse is true. If this network that we had before cost $111 million, the new network we have costs $109 million. Now, the whole idea behind the second part of the problem is to examine intelligently chosen alternatives to an initial starting structure. The way we might have gotten the initial starting structure was a human being sitting down and designing what he felt was a very good pipeline network design. In fact, in our actual examinations of Gulf of Mexico pipeline designs, that's exactly what we did. We took the starting points of the best designs that human beings have been able to come up with. What we then did was to examine reasonable alternatives. For example, a reasonable alternative is a connection from this point to that point. Now, if I make that connection, I no longer have a tree. So therefore, what I have to do is eliminate. I have a circuit now going around here. So I now eliminate one at a time one of the branches in this circuit. Okay? So for instance, if I add that line, I might eliminate that one. I now have a tree again. I would then apply the first process, the optimization process for diameters of pipelines, to see what the cost of the network would be. If the cost of the network was lower, then I would accept that as a potential change, and I would start the entire process again. If the cost of the network were higher, then I would reject that as a change.
Now this process of the delta change is so central to the solution that I'd like to illustrate it in a bit more detail. Well, let me show you how it works in general by looking at the next stage. Now we have the branch AB instead of FB. What we have to do is to look at each vertex in turn. So let's start by taking the vertex F. And we look for the nearest vertex which is not already adjacent to it. Let's suppose it's the vertex E. We then introduce a new branch, FE. And of course, this gives us a cycle. We've got A, B, C, D, E, F, and A again. And then we shall consider trees got by eliminating each branch of the cycle in turn. So we might eliminate AB and get this tree, or instead we could eliminate BC and get this tree, or eliminate CD and get this tree. Now, if we do this for all the branches of the cycle, we can evaluate the cost of each option and we can choose the cheapest. Now, if in fact we remove the branch DC and apply Dr. Frank's diameter optimizing algorithm to the resulting tree, we find a 20-year cost of $108,912,000. Now, this is a further saving of nearly $200,000. Now, what Dr. Frank goes on to do is to do the same thing for each vertex in turn. And he carries on until he gets a tree which is what he calls a locally optimum tree.
When this process finishes, we have a locally optimal solution. The interesting point about a locally optimal solution is you never know whether it's globally optimal or not. For small networks, let's say trees of 5 or 6 or 7 nodes, you can actually exhaustively search for globally optimal solutions. In every case when we did that, the local procedure ended up with a globally optimal solution. To just see what the final network was for this particular set of gas fields in the Gulf of Mexico, this was the final network, approximately $10 million less than the starting one. The entire amount of computer time required to optimize this network was about 15 minutes. 15 minutes for approximately $10 million worth of savings.
Well, you said at the beginning that you began by just looking for a problem to prove you could solve one, and you seem to have been extremely successful with this. Did anybody actually make use of it?
That was the best part of the whole thing. This process was adopted in 1968. At that time, there was something on the order of $320 million of construction in the Gulf of Mexico proposed to the Federal Power Commission. A number of pipeline companies got together and built a system called C-Robin. The proposal to build that system was nothing but the output of our computer program. And what C-Robin did was eliminate $100 million worth of construction and doubled an original capacity proposed for an $80 million network, and in addition to that, reduced the cost of that $80 million network to $72 million, but also carried 3 times as much gas.